Hello, everyone. Welcome to the Elastic Load Balancing Deep Dive session. I'm Pratibha Suryadevara. I'm the General Manager for the Load Balancing Platforms. For this session, I'm joined by Will Rose, who's a Senior Security Engineer at Netflix. So let's dive in. With this session, I'll give you a broad overview of Elastic Load Balancing, and we'll deep dive into two Elastic Load Balancing platforms, the Application Load Balancer and the Network Load Balancer. So let's start at the beginning. So what is Elastic Load Balancing? Elastic Load Balancing automatically distributes your application traffic to multiple targets. The targets that we support today are EC2 instances, containers, and IP addresses. Why do I want to use an Elastic Load Balancer? Let's just briefly look at some of the advantages of using Elastic Load Balancing. On an Elastic Load Balancer, we monitor a whole lot of metrics, like the throughput, the CPU utilization, the memory utilization on your instances, and we dynamically scale both the load balancer and the backends that your applications are running on. When it comes to security, which is a top priority, we support end-to-end encryption. We take care of SSL for you, so you can focus on building the awesome applications. Integration. Elastic Load Balancing is integrated with more than 14 other AWS services, whether it's Route 53 for DNS, CloudWatch for your metrics, AWS Config, and a lot of other services. Let's talk about the cost effectiveness of a load balancer. The Elastic Load Balancer is much more cost effective compared to you instantiating an EC2 instance and running your own load balancer. As you scale, as your service scales, it becomes even more cost effective. So we all started building our applications in the cloud, something like this. I launch an EC2 instance. I run an application. Maybe I'm running a load balancer on the some kind of database on the same instance, and start onboarding my customers. It doesn't take too long to figure out this is not a best practice, either for availability or scalability. Think of what happens if there is a corruption on your application and that instance goes down. The entire customer traffic is impacted. What happens if there is a sudden spike in traffic? Will that instance be able to handle that? So this is what we recommend. You built your application, you've launched it behind an Elastic Load Balancer on multiple instances. If a given instance goes down, we automatically shift the traffic away from that instance to the other healthy instances. If this traffic spikes and you've enabled auto-scaling on your application, we add a lot more instances within the minutes and keep up with the scaling needed. With the introduction of Application Load Balancer and Network Load Balancer, we are starting to talk to our customers about the types of load balancers in general. This is very basic, right? So for those of you who are familiar with the OSI layer, basically there are two types of load balancers, a layer 4 and a layer 7, going by the same OSI naming convention. The layer 4 load balancer, as the name says, runs at the layer floor. It supports TCP, and some load balancers also support UDP. The incoming client connection is just attached to the server connection. The connections are not terminated, no headers are modified. Some load balancers preserve the source IP, but generally the source IP is not preserved. Some load balancers preserve the source IP by prepending it to a proxy protocol v2 header, which is a definition that HA proxy came up with. The layer 7 load balancer is basically an HTTP or HTTPS load balancer functioning at the layer 7. Here, your client connections are terminated on the load balancer and connected to the backends using a pool of connections. Based on the routing features that you've configured on the load balancers, the headers might be modified, and usually the client IP is preserved in the X forwarded for header. So if we've looked at the basic types of load balancers, and coming to the load balancing family, we support both layer 4 and layer 7 load balancers. Application load balancer, operating at a request level, terminates your TLS, supporting HTTP, HTTPS traffic, well suited for your service mesh architectures, and container architectures. The layer 4 load balancer is our network load balancer, which functions at layer 4, suitable for high throughput and can support millions of requests per second. The classic load balancer, which is something that we've had around for a few years, supports both layer 4 and layer 7, but it's not feature-rich. Let's dive into the application load balancer. Application load balancer is a feature-rich layer 7 load balancer that we introduced 2 years ago. So high level, if you want to look at the features of the application load balancer, basically a layer 7 load balancer has a lot of content-based features, whether it's path-based routing or host name-based routing, well suited for your container applications. I'll walk you through the details on why it is suited for container applications. So we support WebSockets for your full duplex communications, whether it's Twitter feeds or force feeds where your clients need to talk to the server and the server is sending traffic back to you. WebSockets is supported on the application load balancer. Before this, on the classic load balancer, you would use a TCP connection to do the similar functionality. The second feature there is HTTP 2 support, which is a newer version of HTTP, which makes your page loads much faster. We've improved our health checks, and we've improved our CloudWatch metrics. The other thing is we've actually implemented an API delete protection. Some of you, if you've been using the classic load balancer for some time, might accidentally delete the load balancer, and I get few calls once in a while asking, can I actually restore my load balancer? Sometimes we can do that if I have not used that IP for some other load balancer, but with application load balancer, we've actually created an API for that and protected it. We've improved the performance of the real-time applications that are rendered behind the load balancer. In a classic load balancer, we used to do a lot more buffering, which caused impact to some of your streaming applications. We fixed that in the application load balancer. Another big change for those of you who are using the application load balancer might have noticed already, the API model on an application load balancer is completely new. I mean, usually we don't break the backward compatibility for our APIs, but when we start designing all these content-based and deeper L7 features on our application load balancer, we figured that it was much easier to start with newer APIs. And so far, the feedback has been pretty good. So just looking deeper into an application load balancer, we'll cover what the API model changed to, the routing features that we support, security features on the load balancer, the availability model that we use for our own load balancer, and also what we recommend for your application architectures, how we want to scale your applications, the integration with rest of the ecosystem, especially containers and service mesh architectures, the monitoring of your applications, and the pricing models, and how you want to migrate from your current classic load balancers to an application load balancer. So let's start with the API models. So yes, we need to start with the load balancer, and then you add a listener to the load balancer. Listener is nothing but a port and a protocol. In this case, HTTP, HTTPS, and we recommend that you use HTTPS. You should have at least one listener per load balancer, and you can have 50 listeners per load balancer. The other resource or the construct that we built for the API is the target groups. Target groups are nothing but a virtual grouping of targets, and the targets that we support are EC2 instances, IP addresses, and containers. So the target group should be homogeneous. You can have multiple of these targets, but the target groups, but the targets within a target group has to be homogeneous. And you actually configure health checks on the target group, and you can associate auto-scaling to the target groups and scale these target groups individually. Focusing on the targets, the target themselves can be EC2 instances, IP addresses, or containers. And you can register the target to multiple target groups using different source ports. you can actually create these abstractions like target groups independent of your load balancer and associate them to your load balancer once you create those load balancers. You can have up to 100 target groups per load balancer and 3,000 targets inside a target group. All of these are soft limits. Most of your architectures and applications should fit in these limits, but if you have any architectures that go beyond these limits, these are all soft limits. So please talk to us, and we can see how we can increase those limits for you. So now we have the listeners, the target groups, and the targets. We have the rules that define how traffic has to flow through these targets. Rules are nothing but conditions and actions. If I walk you through this example, we always have one default rule on the load balancer. And in this case, this is a path-based rule where we are saying if the traffic is coming and matches this path, for example, images, forward it to the IP-based target group. So you can have up to 100 rules per load balancer. And again, it's a soft limit. Talk to us if you want to go beyond that limit. I just want to go a little bit deeper on IP as a target because this is a new thing that we launched this year. With IP as prior to IP as a target, you could support EC2 instances and containers behind your load balancer. With IP as a target, the target can be any IP. That IP can be actually sitting inside your VPC. It can be classic link connected. It can be in the peered VPC, or it can be on-prem, and we connect to that on-prem IP using Direct Connect or VPN. It opens up a lot of interesting architectures for your applications, especially for on-prem kind of workloads. If you have certain workloads that are on-prem, now you can enable those behind the load balancer using IP as a target. A lot of our customers are using this during their migration phase, right? You want to try out, is this the right thing for me to pull all my workloads into the cloud? You want to try out with few of your workloads using IP as a target, and this becomes a migration path for you to pull all your workloads into the cloud. So those are the basic constructs, building the APIs, starting your load balancer. How do you get the traffic flowing into the load balancer? Now let's get deeper into the routing features supported on the load balancer. So content-based routing is the key architecture that we pulled into the application load balancer. With content-based routing, you can use the path or the hostname field inside the header to route traffic. What does it enable? It actually enables a lot of use cases where you can have multiple applications hosted behind your load balancer. It opens up multiple domains that you can have behind a load balancer. If you look at how it was done with a classic load balancer, you had an application, you instantiate a load balancer, you host the application behind the load balancer. If you had one more application, you actually had to launch yet another load balancer and use DNS to route it to one of these load balancers. In this example, if you had the orders and images, two different applications. For these two different applications, you had to instantiate two different load balancers and route them through DNS. With the content-based routing, you can do this with a single load balancer. Both the applications are hosted behind the load balancer, and you will set up a rule saying, if my rule is /orders, forward it to this set of target group. It is /images, forward it to this other target group. Right? So with this, your manageability becomes much simpler. You're managing one load balancer instead of two load balancers. Again, cost effective. You're paying for one load balancer instead of two. It decreases your hourly cost, but the bandwidth remains the same because you're sending the same traffic through. Though the same thing you can do for host names, so both path and host is supported. So you want to think through how you want to consolidate some of your load balancers using this architecture. It's very simple to think about, I want to save, let me bring all my applications behind a load balancer. But I caution, at least the best practice is, think of who's managing this load balancer, what your blast radius is going to be, and what your availability is going to be, right? If you consolidate everything on a single load balancer, maybe you're misconfiguring or affecting somebody else's application or traffic. At least the best practice or recommendation for us is maybe use one load balancer per service or per team. Think about basically the blast radius and manageability when you're actually implementing this content-based routing consolidation for your applications. Another two interesting and exciting features that we launched this year on the application load balancers are redirects and forwards. So if you look at the rules are basically conditions and actions. Prior to redirects and forward, the only action that we supported was a forward action. You set up a rule, we match the rule, we forward it to the right target group. With redirects, you can actually redirect from one URL to another. You can take an HTTP to HTTP, HTTP to HTTPS, HTTPS to HTTPS. But the common use case that we see is HTTP to HTTPS. This actually increases the security profile of your application. Or if you have different versions of your applications, you might want to route your customers from an older version to a newer version. This, again, is one of the key asked features on the application load balancer. And within months of launching it, huge adoption for us. I think this was one of the fastest adopted features on the application load balancer. The next action that we supported a launch this year, a few months ago, is the fixed response. With fixed response, you can actually offload some of the responses to the load balancer and let the load balancer do the response for you, and it doesn't even get to your backends or your clients, right? You might want the load balancer to respond back for a specific error conditions. Set up the rule, same as the path-based rules or the host name-based rules. As long as the rules match, you can let that load balancer handle it and respond back. It doesn't even come to your application. What most of the customers are using this for, like if they're maintaining or something going on with their application, you can set up a fixed error code and the load balancer responds for you, and that can be offloaded to the load balancer. So one other feature, again, customer asked feature, slow start. Slow start works in conjunction with the round robin algorithm, right? So the application load balancer, the way it load balances to your backends or target groups uses a round robin algorithm. So the pain point our customers were seeing here is when new targets are added and the caches on that application or that targets are not warmed yet, it was not able to keep up or it was not ready to take or respond to the requests yet. So what Slow Start does is it actually allows the targets to warm, and only when it's ready, it'll start taking the fair share of requests that should take. So you can go and configure anywhere between 30 seconds to 15 minutes of slow time, and you can actually change or configure what percentage of traffic can go to that newly added target, right? It's all the way from 0 to 100%. So slow start is not enabled on default. You want to go and enable it. So this is suitable for applications that are latency sensitive, right? For example, if you're rendering images and stuff, you've added a new backend, but your backend is not cache warmed yet and it's not ready to respond. Your clients, your customers will see the latency. Instead, you let it warm up the cache. When it's ready, it starts taking the requests. IPv6, we support IPv6 and IPv4 on application load balancer, so it's dual stacked. The traffic coming from the front is dual stack, v4 and v6, and the back end, we support only v4 because most of the applications are not quite v6 yet. So number one priority for us, security. In AWS, we have like 3 number one priorities we talk a lot about: security, availability, and scalability, right? So let's start with how application load balancer will help the security of your applications. So let's start with base TLS. We talk a lot about HTTPS, so base TLS functionality. So the traditional model, you actually set up the DNS for routing your traffic into the application load balancer. You're getting HTTPS traffic into your instances. Usually, you have an admin. You have a choice of your cert authority. You get your signed cert, and you're downloading it into your applications. With the application load balancer, you can actually have the certs downloaded into the load balancer themselves, offloading the TLS management cert rotation into your applications, into the backends. You can integrate your admin into the Identity and Access Management System, IAM, which gives certain policies, who can do what, who can maintain these certs, who can rotate these certs. You're integrating that into IAM, and only certain admins with that privileges will be able to download that certs into the load balancer. One step even further, we now integrated the application load balancer into the AWS Certificate Manager, or ACM. So ACM actually acts as your cert provider. You can bring your own certs, download them into ACM, or ACM can actually give you the certs. And ACM also auto-rotates the certs for you. I think the most common problem for most of your application managers, when are my certs expiring? How do I rotate them? Oops, I forgot, all those that whole automation of cert rotation is done by ACM for you. ACM is completely free, and it's integrated into the application load balancer. We took security even further, right? Yeah, we are bringing the certs, we are managing the certs, but what certs do I use? This changes every day, right? We keep seeing so many vulnerabilities. If you go ask security experts on what certs and policies and ciphers and protocols that I use, everybody gives you the latest protocols, but when you start deploying them, a lot of your clients and web browsers don't support those. And you have varied set of clients, so we have recommendations. We actually, from all our knowledge from S3 and all the other services that we run, we look at the kind of devices that are connecting, we look at the vulnerabilities, we come up with the ciphers and protocols, and actually have a predefined set of protocols that you can pick from when you're creating your load balancer. When you go create the load balancer, you can go click and pick one of these certs that are already predefined for you. And customers always come and ask us to add more certs and policies and predefined policies. We do that. For example, the forward secrecy policies were something that was requested by customers, and we enabled that this year. Going deeper into the security integration on the application load balancer, the application load balancer is integrated into the integrated with the web application firewall. Web application firewall protects your applications from any malicious requests. So web application firewall can block any of the allow or log any of the requests that come through the load balancers to your backends. With this, you can actually protect yourself from any SQL injections. You can protect yourself from any bot scripting. And as WAF adds more rules and policies and integrates with any of the third-party providers, you get that by default on the application load balancer. So it's tightly integrated. All you have to do when you're creating a load balancer is choose that you want your traffic to go through the WAF, and it flows through the WAF. And any rules additions, any enhancements that are done on the WAF, nothing needs to be done on the application load balancer. One more thing that we have recently launched is actually tight integration on the console for both WAF and AWS config. So from the application load balancer console, now you can actually deep link into the WAF and go and configure the additional things if you want to from the application load balancer console. The same thing can be done for AWS config. This is something that we launched just a few weeks ago. Continuing, pretty excited. This is, again, one of the most asked feature, server name indication. We talked about how with the content-based load balancing, the content-based routing features, you can host multiple domains and applications behind the load balancer. One of the key asks was, can I have a unique cert for each of the applications that I'm hosting behind the load balancer? With SNI, each listener can take multiple certs, and you can have unique cert for each of the applications that you're hosting behind the load balancer. Going beyond, we even have, if your host name matches to multiple certs, we have a smart cert algorithm running that picks the right cert based on your client behavior. We support both RSA algorithm and the newer and faster ECDSA algorithms. We have a limit of 25 certs per listener, but again, soft limit, please let us know if you want more. But think again, it comes back to that blast radius. Why we landed with 25 was that's where we saw most of our 99.9% of our customers not needing more than those 25 certs based on the number of applications they're hosting behind. Before we supported SNI, you would use maybe SAN certs or wildcard certs to do the same thing, but those were much tedious to maintain. SNI takes away that manageability part of it. One other feature that we launched middle of this year, very excited about this feature. We actually integrated authentication onto the application load balancer. With authentication, basically we authenticate on the load balancer any of the applications that are sitting behind the load balancer. So with few clicks, you can integrate any of OpenID Connect-based identity providers onto the application load balancer. So the authentication is happening on the load balancer, and you can use any ID provider, social ID providers like Amazon, Facebook, Google, any of those can be used for authenticating. We went even further. This is for OIDC, which is web-based applications. We've extended it to even enterprise-based applications that use SAML. So to bring SAML support, we integrated application load balancer with AWS Cognito. So Cognito brings you the SAML and OIDC support. So with the auth feature, you can integrate your own IDPs as long as they're OIDC compliant, or you can use any IDPs and SAML if you integrate with Cognito. So Facebook actually used this feature to simplify their application architecture inside Facebook. So at this point, I'd like to invite Will to go through and walk us through their use case and how the authentication on the application load balancer simplified their application security architecture.
Thank you, Pratibha. So as you mentioned, my name is Will Rose. I'm a senior security engineer at Netflix. And more specifically, I work on the group that works on our identity platform for all of our workforce and partner authentications. Even more specifically, we focus on the interactions between humans and browsers. So underlying all of that is kind of a fundamental principle that we think developers shouldn't have to worry about managing user logins in their applications. And we think the users shouldn't need to worry about logging into each and every site independently. That's kind of what motivates us to secure the infrastructure there. So what we're providing is a workforce identity platform as a service. Sounds really interesting, I'm sure. Now, the first thing we need to do is to federate every application onto our platform. So adoption is a major thing we need to pave and make smooth and easy. Otherwise, a lot of the benefit or all of the benefit is lost. So federation's at the core of that. Now, before I overuse that word federate, I should probably define it a little better. Basically, when I refer to federation, I'm talking about the process of having your application defer the login process to another provider, let them interact with the user in a standardized way, and then trust the response from that provider that says, yes, this is Will, and he's just authenticated, let him into your application. So that handoff is the federation. In the wild, you'll see this often as a login with Facebook or a login with Google button. That's federation. If you ever click one of those buttons, that's what's going on behind the scenes. So we've been federating our applications for quite a while. Originally, we did everything on SAML, starting like 4 or 5 years back, and have more recently moved on to some of the newer standards, OpenID Connect specifically, which is an extension of OAuth. So we've been in the federation game for a while. And it's always been a standards-based, even if we're shifting from one standards to another. Now, Central to getting all of our developers onboarding their application onto our identity platform, we've really invested in developer self-service. We really think the only way to get true adoption is to make it easy and painless for our developers to register their application in real time without any kind of heavy provisioning process or approval process in the middle. On the user side, we offer the value of single sign-on experience, so they don't have to keep authenticating. So the developers get easy registration, the users get easy login. Now, that tells a pretty good story for how we make a standardized, centralized identity platform. The flip side of that is that each application needs to integrate with that standards protocol. Now, we have a lot of different applications, and we have a lot of different technologies that they're built with. So this really stems from a core value of Netflix we call freedom and responsibility. And we apply it everywhere, including application developers and how they develop and what they develop with. So they have that freedom to choose their technologies. However, with that freedom comes great variability. We have many languages, many frameworks, and all of them need to interoperate in a standard way with our platform. So we need to find a good way for all of these different permutations and integrations to talk to us. So what are our options? There's some challenges there. The first obvious option would be to just use client libraries for everything. And that works. You can do that. If you have a handful of frameworks and application languages, if you have a small number of individual applications, managing and succeeding with a broad ecosystem of applications gets more challenging, however. So with frameworks and languages in particular, always there's fluctuation. There's new ones coming and going in and out of fashion. There's open source options, often many, so picking the best one sometimes isn't necessarily a great one. You have a lot of variability in how they implement the spec, the completeness and the quality. You have potentials for vulnerabilities and bug fixes that need to be tracked and mitigated. And even at the end of that, we still have to figure out how to get each and every library configured the specific way for that specific protocol in that specific language. There's a lot of opinions about how that should be done, and they're all a little bit different. So that ends up creating some developer friction, and we'd prefer not to have that. So the native client libraries works for an individual application, not so well for hundreds. So other options. We could use authenticating proxies. This is actually a pretty popular pattern, and it works really well. It does move that responsibility further up the stack and away from your application layer. However, it also has some trade-offs. It creates an additional layer of critical infrastructure you need to maintain. Now, that means additional cost, complexity, failure modes. Your application's only as good as that authentication proxy layer. Lots of bottlenecks, lots of room for things to go wrong. So makes things easier for the developers, doesn't really make things easier for us. So between those two options, we had to choose one. We went with none of the above and decided we would kind of keep thinking about alternative solutions. And this is us thinking. So we had a kind of crazy idea. These application load balancers that Amazon making have been getting more and more sophisticated and more and more features. What if we considered auth to be yet another function of the application load balancer? If you look at it through the right lens, you could consider authentication some undifferentiated heavy lifting. It is standardized. It could be implemented in a common way here. So being an OpenID Connect shop and already leveraging application load balancers, we came to Amazon and asked if they had anything in the works. And here's what they cooked up. It's OpenID Connect natively implemented on the application load balancer. Now, behind the scenes, you get some new capabilities that look like this. At the heart of it is a new action type for application load balancers. So the actions are attached to rules, the rules themselves are attached to listeners, and all the routing content or path or whatever it may be, all that still applies. The Authenticate OIDC action, though, does a lot of heavy lifting for you under the hood. So the first thing it can do is obviously make sure that a user has been previously authenticated. And if it hasn't, it can redirect, following the OpenID Connect protocol, to the identity provider for which you've configured that action. It's up to the provider and the user to negotiate whatever that authentication looks like. Perhaps there's second-factor authentication, username and password reentry. Perhaps they just get redirected right back and don't even see a login prompt. Now, the return response, again, follows the OpenID Connect standard. The Authenticate OIDC action takes care of all of the handshakes and negotiations to take that response and create an actual session. It manages a session for you, creates an encrypted cookie, and packs all of the state that was returned from your OpenID provider into that cookie. And for all subsequent requests, it passes that authenticated session data through the Authenticate OIDC action to whatever action is downstream. Now, typically that's just a forward action, but it could be others. More coming, I'm sure. Now, along the way, since the session data that the load balancer is managing is now been validated, it can pass that context down to your target application. That takes the form of 3 different headers. There's a plain text identity header, which is just the email of the user. There's an access token, so again, this is OAuth, and since OAuth is built all around access tokens, an access token is issued as well in OpenID Connect, and it passes that along as well in case you or your application have a future use for it. And then there's also a OIDC data header. And this is really where whatever contract your OpenID provider configuration is fulfilling is being represented. So this is a signed and encoded JSON Web Token. The JWT is the common abbreviation you'll see. That can be decoded and validated by your backend application to get a lot more user metadata about that authenticated session. It's up to you what you put in it, but common things are like email name, first name, last name, perhaps your division, perhaps any groups you may be in. It's really up to you to how you compose that, but that context is provided to your target application as well via that data header. So the ALB is handling a lot. That's just the OpenID Connect option. That's the one we use. There's still another one that Amazon threw in for free, which was the Authenticate Cognito option. This is great because it extends beyond just OIDC. It gives you, via Cognito, kind of a way to bridge into SAML identity providers, social login providers like Google and Facebook, and even authenticate the users from the load balancer against your own Cognito user pools. So a lot of options there for how you want to authenticate users. So it's been about 6 months since this has gone GA and we've been using it. It's gotten pretty good adoption so far. We've updated our Spinnaker application, which is an open source CI/CD kind of delivery and management tool. Built by Netflix, open sourced, now getting a lot of input from other companies like Google and Amazon as well. Very cool tool. If you want to check it out, I highly recommend it. There is an integration now in Spinnaker that allows native configuration of the load balancers to provide all of the OpenID Connect configuration in just a couple clicks. That has really kind of given us the best of both worlds. We have a pretty easy provisioning process by which our developers can register their applications with our platform, and now we have a simple, lightweight way and standardized way for them to integrate their application using whatever framework or language they have in a consistent way because the load balancer is handling it all. The best part is there's no real new infrastructure required. We're not managing the authenticating proxy layer. We're not managing the diversity of OpenID Connect libraries. We're using infrastructure we would have been using anyways, and we're getting this really big added benefit. So this has become our recommended integration path for all applications who want to federate the authentication of their users with our identity platform. And it's been working very well. So I encourage you to give it a try. Tell us what you think. That is my time for today. I will be available after for questions, and my email will be available as well if you want to reach out to me. So thank you very much. Thank you.
Thanks, Will. Thanks for walking us through the auth architecture at Netflix. Continuing on the security features, I want to briefly talk about 2 other features that we launched recently. One is capability for adding tags to your load balancers and your target groups. You can go and add tags to your load balancers and target groups, filter them, and apply configurations only based on the filtered resources that you have. One other feature that we launched recently is the granular fine-grain access control for your resources. whether those resources are your load balancers, targets, target groups. So you can actually integrate with IAM and provide much granular access control. For example, a simple example of who gets to delete the load balancer, right? You can go and define a very fine-grained policy on who can do what to your resources. So now let's get into availability. This is the number 2 highest priority, or like when we mentioned security, availability, and scalability, let's get into the availability part of things. So availability of the load balancer and the backends is very critical for your application traffic and for your customers. So for our own load balancer, we always launch at least in 2 availability zones. And the traffic enters into one of these using DNS. So some of the clients, like Java clients, actually cache the IP addresses. Hence, you might see imbalances in the traffic distribution into each availability zone. Cross-zone load balancing solves that problem. What we do is we actually prevent that imbalance, evenly distribute the traffic across these 2 different or n number of availability zones that you create. We go even further. If you have more number of instances or higher compute in a specific availability zone, we forward more requests to that availability zone. For example, if one availability zone has 3 times more instances, we forward more. You are not paying for any cross-zone data charges, so this is completely free. And the third thing is cross-zone load balancing is always enabled by default on the application load balancer. So the other availability part of it, which is very critical, is the health checks. So you want to, health checks actually fail away traffic from impaired nodes. You want only healthy nodes rendering traffic to your customers. So health checks, just a quick look. You set up your instances, traffic is flowing. One of the instances becomes hot for whatever reason, more traffic, something crashes. Load balancer detects that within seconds, fails away that instance, routes the traffic to the rest of the healthy instances. As soon as the instance becomes healthy, it comes back up, you start routing traffic. So all this can be completely automated. Going a little bit deeper in the kind of health checks that we provide on the load balancer, this is an application load balancer. So we can provide HTTP health checks. You can configure the frequency and failure threshold for each of those health checks. The depth and accuracy of the health checks. One thing I want to quickly call out is in a classic load balancer, when all the health checks on your backend failed, we would fail close that request. In application load balancer, we changed that behavior. When all the health checks fail, we fail open. The reason why we did that was, if you configure to have a very deep health check, maybe your health check is going somewhere out and it takes longer and it has more latency, we didn't want to fail that. Hence, we did a fail open behavior. But general recommendation is think carefully about what kind of application you're running behind, what is the best health check per application. Generally, we recommend not go very deep in configuring your health checks. One other enhancements that we did is you can customize the error response that we get back when you actually fail those health checks. And the reasons for the health check failure are actually shown on the console right now. This is one of the pain points we got a lot of support cases for. Quickly getting into scalability, we always recommend that you configure auto-scale inside your target groups. With auto-scaling, you can actually launch, configure, and serve with new instances within minutes, right? So you can predict the scale of your application. Please go and enable auto-scaling. The container integration. One other, as you're looking at microservice architectures, we are looking deeply at how we integrate or how we enable some of those through the application load balancer. The first thing we introduced is you can actually register multiple of the containers that you have running in that instance using different dynamic source port mapping into the application load balancer. That's the basic integration. The other part is, because it's tightly integrated with EC and EKS, any features, enhancements like Fargate and additional features that are added on the container platforms are just enabled. You don't have to do anything. It's just tightly integrated. One other thing that we've recently launched is an ingress controller functionality. So with application load balancer, you can use not just with ECS and EKS, but you can bring your choice of container technology like Kubernetes. Because of the deeper L7 features that we have on the application load balancer, the application load balancer is ideal for an ingress controller kind of functionality. We are actually iterating a lot more on this. We've actually published the first one onto the GitHub, and we'll continue to iterate and push a lot more features into the ingress controller functionality. So again, auto-scaling works really well with the container technology also. With containers, again, like you're using it, just that the scaling happens much faster, not minutes, but within seconds. Now that you've built scalable, secure applications, let's look at how you monitor them. I mean, you cannot manage an application that you cannot monitor, right? So monitoring for us is not just metrics, but it's deeper into logs and how you debug your load balancers. For Elastic Load Balancing family, we've always pushed a lot of metrics into CloudWatch metrics. So this gives you an overview of how your traffic is flowing, the health of your backends, your application health, and your load balancer health. You can actually set alarms if any of these metrics is not within the range that you expect it to be. One of the things that we're supporting now on the metric side is percentages. For managing AWS scale, we use percentiles a lot within AWS. Let me walk through a simple example. If one of your applications is latency sensitive, and customers will see an impact if your latency is more than 100 milliseconds. So you can set at least one alarm, if not many alarms, if you want to watch that metrics. What we do for those kind of applications is, if I'm expecting 100 milliseconds, maybe I want to watch at a 50 millisecond metrics. Maybe I'll set up a P99.9 metrics, which is a less severity metrics that I can look at. If my latency is going beyond 50 milliseconds, I can set up another metric for P99, if it's going an urgent metrics, an urgent alarm that I can monitor right away if my latency is going above 50 milliseconds. Inside AWS, we use this percentile metrics and alarms based on different percentiles very extensively to work at our scale. We keep pushing these metrics at 1 minute granularity into CloudWatch. Metrics gives you an overview, but if you want to go deeper, ALB provides huge amount of access logs. So you can go very granular. You can look at the request times. You can look at the client IPs, the latencies, request paths, server responses. Very helpful when you're doing offline analytics and debugging of your application. Any of the access logs are very helpful for dive logging and looking at after you have an impact or an LSC kind of situations. It is very helpful to see how we want to improve this. These access logs can be pushed to an S3 bucket every 5 minutes or 60 minutes, and it's configurable. So we've talked a lot about application load balancer. I just want to put everything together. So tightly integrated with a lot of AWS services, all the way from Route 53 to WAF to Cognito to the certificate manager, supports deep layer 7 features, supports SNI for your cert management, supports container integration, and supports on-prem kind of devices using IP as a target. Getting into the pricing part of it. Application load balancer, you always pay for what you use. Primarily, there are two components to the application load balancer pricing. One is the hourly cost, and one is the LCU. The hourly cost comes out to $16 per month. And it's actually 10% less expensive than what you pay for a classic load balancer. The load balancer capacity units, or LCU, has 4 components to it. You get 25 new connections per second for one LCU. You get 3,000 active connections, 1 GB of traffic, and you can evaluate 1,000 rules. So what we do is we monitor all of these 4 metrics, and we bill you for the max of it. We are not billing you for all 4 of them. we bill you for the max of it. Most of the applications are actually get LCU'd on the bandwidth angle. So last thing, we talked about all the features of the application load balancer. How do I migrate? We made this very simple for you. Create an application load balancer, migrate your backends, change the CNAME. You can actually wait it, or you can actually do a simple CNAME change. You have a lot of tools, and we've actually created a wizard on the console that does the configuration movement also for you. So migration is very, very straightforward. All the tools that help you with the migration are pushed to the GitHub. Now let's get into our layer 4 load balancer, which is the network load balancer. The network load balancer is a layer 4 load balancer. Millions of requests per second, high throughput, and very low latency. So network load balancer is built with our Hyperplane technology. So that is how we achieve the ultra low latency. The Hyperplane technology is something that is our own SDN technology that is built deep into our VPC core. So that is how we achieve this ultra low latency. Once you set up the load balancer after the connection time, most of these connections actually are completely passed through, and you won't even see that there is a load balancer or a proxy sitting in between. The load balancing algorithm that we support on, basically it's a flow-based load balancing. We actually hash the flows based on the 5 tuples and the sequence number. Let me walk you through some of the features on the application load balancer. The first critical feature, before the features, the resource types and the APIs on the network load balancer are exactly same as the application load balancer, same listeners, target groups, and targets. So we'll go deeper into each of these features, the static IP, the preservation, and the platform features, which are availability, monitoring, pricing, and migration for the network load balancer. So let me start with the static IP feature. With network load balancer, you get a single IP for availability zone. In addition to that single IP, if you don't want this IP to change for the life of the load balancer, you can assign an EIP from your VPC, and we will take that and assign it to the network load balancer. And if for whatever reason you delete the load balancer, we return the EIP back to you. The single IP, static IP, enables a lot of use cases. So one simple use case is you can use that single IP to whitelist your firewalls, right? You're dealing with single IP, your IP management becomes much simpler, and managing or configuring your load balancer becomes much simpler. One other use case that we are seeing a lot is actually zeroing out a bill for a certain, maybe a mobile application or any specific application that you want. So this is a simple example of a network load balancer with each of them having their unique EIPs per availability zone. So the next critical feature on the network load balancer is preservation of the source IP. So the network load balancer is a complete pass-through device. We actually preserve your client IP and send it back all the way to your targets. So a lot of use cases open up with it. One that I want to highlight is if you want to set up security groups on your backends and allow traffic only from a certain CIDR group, you can use the client IP preservation. One thing I want to call out here is client IP is not preserved if your backends are IP as a target. We are doing that because that IP can be outside of your VPC and we don't know what it is. But if your applications have to enable that, please let us know and we can whitelist you for enabling that feature. The way we enable that is we'll add that IP to the proxy protocol v2, and your applications can read the client IP from there. And in addition to that, if you want to natively preserve it, let us know and we can whitelist you for that feature. So let's quickly look at a simple firewall example, real-world example, where in this example I have 2 load balancers, network load balancers, external load balancer front-ending a set of firewalls, and an internal load balancer front-ending a set of web servers. For the firewall fleet, because of the single IP, all the firewall configurations becomes very simple. You can actually whitelist a single IP, and you can horizontally scale the firewall fleet because what is exposed is only a single IP. On top of it, since we are preserving the source IP, and if the proxy layer is NATing, whether it's a firewall or a WAF layer, you have the IP that you want to NAT with. Similar thing with the internal load balancer. We preserve the source IP. So again, you're dealing with a single IP, and that's the only IP that you want to whitelist with. So let's get into the availability model. Just like the application load balancer, network load balancer also supports health checks. But one additional thing on the network load balancer is a network health check in addition to the application health checks. The application health checks work exactly like on the application load balancer. You can configure HTTP or TCP health checks or HTTP health checks. You can customize the frequency and the failure. But the additional thing on the network load balancer is the network health checks. What network health checks do is actually monitor the behavior of your backends, and if you see any behavior changes, we fail away within seconds. You want to use this for any fast failover kind of use cases. So this is new on a network load balancer. So this is just a simple example. You have traffic flowing through 2 EIPs in 2 different availability zones. One of the availability zones is down or your backends are down. We automatically remove that IP from DNS, and you're forwarding traffic only to the healthy zones. Going deeper into the metrics, similar to application load balancer, network load balancer pushes a whole lot of metrics. I want to highlight the metrics that are new on the network load balancer. So you want to look at the active flow count, you want to look at the new flow count, and you want to look at the process byte. The process bytes include both the request and response, and one point I want to highlight here, it includes the headers also. Since network load balance is a complete pass-through device, most of the resets are basically just passed through by the network load balancer. The client resets are passed through, the target resets are passed through. In addition, we have any resets that are done by the network load balancer has a new metric. Last, for the host health count, to look at how available your application is, you want to monitor both the healthy host count and also the unhealthy host counts. Just like the application load balancer, we provide, instead of access logs, we have flow logs on the network load balancer. If you want to go deeper, debug your applications, you want to look at the flow logs. Just want to touch the pricing model. Since the application load balancer is a high throughput, millions of connections per second, we price the network load balancer a little bit differently. So the hourly price is the same. It's 10% cheaper than the classic load balancer, but same as the application load balancer. But the LCU model is a little bit different. In the LCU here, you're actually getting 800 new connections per second instead of the 25 new connections on the application load balancer. And you get 100,000 active connections instead of the 3,000 active connections on the application load balancer. Because it's a high throughput, high bandwidth, we priced it differently. And the bandwidth price is also 25% cheaper than the application load balancer. So it's ideal for these high throughput, high connection, long living connection kind of applications. So migration, similar to the application load balancer, exactly the same. You create a new load balancer, you move your targets behind the load balancer, change the CNAME. Lot of tools available to help you with the migration. We talked about application load balancer, network load balancer. The question is, which one should I use, right? So if you look at just a summary of the features, application load balancer being a layer 7 feature-rich load balancer, you want to use that for any of your application or microservices-based architectures. It supports the web sockets, it supports authentication, container integration, IP as a target, SSL termination. For TCP workloads, you want to use a network load balancer, high throughput, preservation of the source IP, single IP. And for your If you still have classic network, classic link-based applications, you want to continue to use the classic load balancer. Just to summarize, TCP loads use the network load balancer. For all other layer 7, use the application load balancer. And continue to use the classic load balancer for if you have the classic link or classic workloads, but we recommend you to migrate to a network load balancer or an application load balancer. Thank you. Hope it was helpful. Both our handles are here, Will's and mine. If you have any other questions, feel free to send me a note, and I'll be around if you have any other questions. Thank you.